Hello students, today we'll talk about Van-de-Graaff generator. We'll see on which principle Van-de-Graaff generator works, and later on we'll discuss construction and working of Van-de-Graaff generator. So let us start. To understand today's topic, we need to be clear with the following points. If we consider a charged shell of radius r and charge q, we know that to find out its potential at any point on the surface of shell or at any point inside the shell, we can use this formula kq upon radius. The potential of the charged shell on the surface is kq by radius, and it is same at any point inside the shell. Inside the shell, potential remains same. But if you are at any point outside the shell, then the potential due to the shell at any point outside can be given as kq upon distance of the point. The denominator here is distance of the point from center of the shell. So with the two formula clear, we can start with today's topic. Consider a shell of radius r, and let the charge on the shell be q, small q. 2 points A and B uh, around the shell. B is at distance small r from the center, and A is at distance capital R from the shell, the center of the shell. How much is the potential at A point due to this charge Q? So if we denote it with VAQ, now we know that this point is outside the shell, and so if I want potential at point A due to this charge small q, then it should be kq upon distance, means kq by capital R. Similarly, if I want potential due to this shell at point B, if I denote it with VBQ, what should be the expression for VBQ? kq upon radius. Radius is smaller, and hence it is kq by smaller. Let us consider another case. Now I have a shell of radius capital R, and again I have charge on the shell. Let the charge now on this shell be capital Q. So now I consider again 2 points A and B. Now A is at distance capital R and B is at distance small r, just like previous case. And now again I want potential at A point due to the charge Q. I want potential at point A due to charge Q. How do we find it? So now A point is on the surface of the shell, and so what should be the expression? KQ by radius. Radius is capital R. So K capital Q by capital R. And similarly, if I want potential at B point due to this charge capital Q, then now B point is inside the shell, and then what should be the potential at B point? KQ by small r or KQ by capital R? When you are inside the shell, the potential is KQ by radius. If you are outside the shell, potential is KQ by distance. So for now, VBQ will be KQ by capital R. Be very much careful here. You are inside the shell, and hence potential will be KQ by radius. Now, what if we consider two concentric shells, and again if we consider the 2 points. So if I have the same two shells with the same charges small q and capital Q and same points A and B, if I consider, now I know that potential at point A due to charge on smaller shell can be given as kq upon capital R. And what is the potential at A point due to the charge on bigger shell? That is kq by capital R, and similarly charge at B point due to smaller shell is kq by small r, and at B point what is the potential due to bigger shell? Kq by capital R. So now we have 4 formula, but as we have 2 shells, at A point we have potential due to capital Q, at A point we have potential due to smaller shell. So how much is the total potential at point A? How much is the total potential at point B? So for that we need to sum up potential at A point due to smaller shell and bigger one. So we have these 4 equations, and now I want potential at point A. So if we denote it with VA, it is KQ by capital R plus KQ by capital R. Now first Q is charge on smaller shell and second Q is charge on bigger shell. Similarly, if I want potential at B point, it will be KQ by small r plus KQ by capital R. Okay, and charges are also different. So now if I want potential difference, if I take VB minus VA, what would I get? See, now I have KQ by R in first bracket also and KQ by R in second bracket also, which will be cancelled out if I take subtraction. And hence VB minus VA is K small q by small r minus K small q by capital R. Taking KQ out, this is what we get. So what does it mean? Now look at the first term here, 1 by R. Now this is smaller radius and hence this number will always be larger than the second number, 1 by capital R. And that indicates that VB will always be greater than VA. It means that you deposit slight amount of charge on smaller shell and it will go at high potential, and outer shell will always be at low potential. And then what does it mean? That means that charges will always go from inner shell to outer shell. And this is the principle for working of Van-de-Graaff generator, that you deposit small amount of charge on inner shell, and if there is connection to outer shell, charges will automatically flow from inner shell to outer shell. And that is how you can deposit large amount of charge on outer shell, which can in turn produce large electric field, and large electric field can exert force on charge particle, and you can accelerate charge particle. So that is the principle of Van-de-Graaff generator. So in conclusion, we can say that if we consider two concentric shells, say one is having radius capital R, other one is having radius small r, and if we choose 2 points, A on outer shell, B on inner shell, then the potential difference between these 2 points can be given as KQ bracket 1 by small r minus 1 by capital R, and this equation indicates that VB will always be greater than VA, and hence inner shell will be at higher potential, outer shell will be at lower potential, and then charges will flow from inner shell to outer shell. So what is the working principle of Van-de-Graaff generator? The principle is charges flow from higher potential to lower potential. So that is the working principle of Van-de-Graaff generator. Van-de-Graaff generator is a device which is used to produce high electric field, and with high electric field we can accelerate charge particle. In next video session we will see construction and working of Van-de-Graaff generator. Thank you.